Welcome to CSAI Think Tinker Learn. Today, we're tackling one of the most sophisticated topics in the data layer, distributed SQL. We are teaming asset correctness with global scale. This video is part of our System Design Essential series, where we provide high-level mental models of complex architecture. These lessons are intentionally kept concise to give you a big picture without getting bogged down on implementation details. If you want a deeper dive or if you prefer text on a specific topics, uh, please visit my site. The link will be in the description. And if you want any kind of a deep dive here on this particular channel, please let me know in the comments and I'll make sure I get that video out for you. Now, let's start with today's episode. Now, distributed SQL exists to solve a macro problem, balancing on the tightrope between a traditional SQL node SQL, traditional single node SQL and NoSQL. Single node SQL is ACID perfect but limited by the capacity of a single machine. NoSQL offers high throughput and horizontal scaling, but often at the cost of eventual consistency. Distributed SQL occupies the hardest middle position, marrying transactional safety with multi-node horizontal scaling. The critical failure point it solves is application level sharding, where you no longer have to push complex cross-shard join logic into your application code. To understand this system, we must start with the CAP theorem. In the presence of a network partition, which is a physical reality, a system must choose between consistency and availability. Distributed SQL is strictly CP. In a financial or a mission critical system, a service unavailable error is infinitely better than a transferring money twice or corrupting a ledger. It chooses safety and correctness over 100% uptime during a network failure. Under the hood, we tear down the engine into a clean three-layer stack. At the top is the SQL or the query layer, the interpreter that speaks standard syntax. In the middle is the transaction layer, the referee that ensures atomic consistency across nodes. At the bottom is the distributed storage layer or the warehouse that holds the raw bytes. Moving between these layers over a network introduces the consensus stacks, the latency overhead required to keep all the nodes in sync. Let's look at layer 1, distributed storage. Most of these systems use a key value store like RocksDB underneath. Data is chopped into small range shards, usually around 64 MB each. The system handles auto splits and merges transparently as data grows. The senior insight here is hotspotting. If you use sequential keys, you will flood a single range before it can split, creating a massive bottlenecks that the application can't easily see. Layer 1.5 is the Raft consensus protocol. Every 64 MB range belongs to its own Raft group, typically with 3 to 5 replicas. A leader takes the write and syncs it to the quorum, a majority of followers, before acknowledging success. If you lose too many nodes and lose quorum, the system halts writes entirely. This prevents split brain scenarios where two nodes might think they are the leaders simultaneously. Layer 2 is the transaction layer, acting as a referee. It uses two-phase commit to coordinate transactions that span multiple shards safely. It also utilizes multi-version concurrency control to allow non-blocking reads. In this model, readers don't block writers and writers don't block readers. However, beware of high contention, multiple transactions fighting for the same row. This can lead to deadlocks and aborts. Now for the hidden complexity, millisecond clocks. Time is the hardest problem in the distributed system. Google Spanner uses TrueTime, relying on GPS and atomic clocks to minimize uncertainty. Others use hybrid logical clocks. If clock's drift exceeds a specific threshold, it causes ordering anomalies. Millisecond dictates the exact order of transaction across the globe, and you cannot rely on a standard server clocks to keep them straight. Layer 3 is the SQL layer, the interpreter. It generates the abstract syntax tree and uses a cost-based optimizer to find the best execution path. The most critical optimization here is the predicate pushdown. You must always send the filter to the data nodes. Never pull the raw data back to the query layer to filter it. Pulling millions of rows over the wire to find one record is an architecture failure. In the consistency spectrum, most distributed SQL syntax default to snapshot isolation for performance. While it protects against dirty and non-repeatable reads, write queues can still sneak through serializable. Is the, is the only absolute shield against all anomalies, but it is a deliberate opt-in because of the performance cost. Systems like Google Spanner target external consistency, ensuring that transactions appear to happen in real time under globally. Who are the major players? CockroachDB superpower in geopartitioning allows you to pin rows to specific EU regions for GDPR compliance. TiDB focuses on HTAP, hybrid transactional and analytical processing, running row-based and column-based storage together. Yugabyte targets PostgreSQL compatibility, running standard Postgres query layers over its own DarkDB storage engine. Choosing the right one depends on your specific bottleneck. Before you deploy, understand the entire patterns. Don't use distributed SQL for small scale apps. Plain PostgreSQL is faster. Don't use it for pure analytics. Snowflake or BigQuery have superior scan formats. And if your system can tolerate eventual consistency for things like social media likes, stick with Cassandra. Every write in distributed SQL requires a network round trip for Raft quorum. You cannot run the outs you well, you cannot outrun the speed of light. In a system design interview, if you are asked to design a global financial system, draw these three layers. Use HLC for ordering, range sharding for distribution, and Raft for application. Now, a question for you. Have you ever tried to scale a traditional SQL database using manual application level sharding? And what was the hardest part of managing that complexity? Let me know in the comments. If this blueprint helped you, please like, share, and subscribe, and turn on that notification icon so that you get notification for the remainder of the series. Check out our site for more essentials. See you in the next one.